Page 3 of probability. Illustrate on a two-dimensional grid the sample space for rolling, we're doing A and C by the way, rolling a die and tossing a coin simultaneously. So we're going to use the grid, and the grid, if we roll a die, is going to be 6. A typical dice has 6 sides, so it's going to be 6 wide. And then tossing a coin would be 2 wide. So there we got that. So this is the coin, and then this is the die. Okay, so the coin has heads, tails, and the die has 1, 2, 3, 4, 5, 6. Okay, and then if you want to, you can like draw like lines going to connecting the labels to each of these. Something like that. Okay, now do rolling a die and spinning a spinner with sides A, B, C, D. Okay, which looks kind of like that. Okay, so in this case, we've got rolling a die would be 6. And then spinning a spinner with 4 sides A, B, C, D would be 4. So basically it's a 4 by 6 sample space or grid. So the left side, we could label it with the dice outcomes, and then over the top we will do the spinner outcomes A, B, C, D. And then we could draw the lines to the points if you want to. Okay. 3A and C. They illustrate on a tree diagram the sample space for tossing a 5-cent and 10-cent coin simultaneously. So even though one of them or both of them are happening simultaneously, with a tree diagram, it's easier if we consider them two separate events, one happening slightly earlier. So we could say like maybe the 5-cent coin toss is happening first, and we'll get heads, tails from the 5-cent toss, and then the 10-cent toss would be the next step, and maybe it would, let's see, 10 cents would be heads, tails also. Okay? What about for C? Twirling 2 equilateral triangle spinners labeled 1, 2, 3 and X, Y, Z. So we'll say that we'll do the 1, 2, 3 spinner first, has 3 outcomes, and then after that we will do the X, Y, Z spinner. And you see how you have to draw the tree, identical trees from each one of the branches for X, Y, Z. X, Y, Z. X, Y, Z. All right. So that was C. Yeah, we're just doing A and C. 22C, theoretical probability. The following probability calculation, where the number of favorable outcomes is divided by the total possible outcomes, only works when the probability of each outcome is equal. Okay? Otherwise, each one of the probabilities would need to be replaced with the probability of that event happening. Since they're all the same, then we could just take the number of events divided by the number of possible outcomes, and you'll get the probability. So 2 events are complementary if exactly one of the events must occur. If A is an event, then A dash is the complementary event of A, or not. It could also mean not A. Okay? So A or not A totals up to 1. That makes sense, right? So give an example of a pair of complementary events. What about, let's see, wins the game or doesn't win the game? You may say, why don't you say win the game and lose the game? Well, you know, sometimes there's tie the game, so I want to have a complementary event which takes care of every other possibility besides the event itself. So that's why I said doesn't win the game, so it's more complete. Okay, page 4. I told you these are pretty quick pages. A marble is randomly selected from a box containing 5 green, 3 red, and 7 blue. Determine the probability that the marble is A red, B green, C blue, etc., etc. Okay, so these we're going to do all of them. So what's the total number of marbles, by the way? 5 green, 3 red, 7 blue. So the total looks like it's 15. So all these probabilities could be divided by 15. So like, what's the probability that you'll draw randomly a red marble from the box? It would be the number of red marbles, 3, divided by total marbles, 15. What about green? It would be 5 divided by 15 also. What about blue? It would be 7 divided by 15 also. What about not red? Not red would be green and blue, which would be 12 divided by 15. What about neither green nor blue? Neither green nor blue. That would mean red, so that would be 3 out of 15. Another way you could do this one is, you could say, oh, well, green and blue would be 5 over 15 plus 7 over 15, and that totals up to 12 over 15, right? And then you say, okay, now I'm going to say 1 minus 12 over 15. That will give me 3 over 15, and that happens to be this, right? What about the probability that we're going to draw green or red? Green or red. So that would be 8 possible marbles you might draw. 8 divided by 15. Okay. What about 3? Here we're going to do A, C, E, and G. A dartboard has 36 sectors labeled 1, 2, 36. Determine the probability that a dart thrown at the center of the board will hit a sector labeled with a multiple of 4. Okay, so how many multiples of 4 are there between 1 and 36? Well, there's 4, 8, 12, 16, 20, 24, 28, 32, 36. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. So that would be 9 out of 36. So there would be a 1/4 chance that you would hit a multiple of 4. That makes sense, right? 1 in 4 numbers is a multiple of 4. What about C? A number greater than 20. A number greater than 20. So that would be 36 down to greater than 20. So it would be 21 to 36. 21 to 36 is 16 numbers. So that would be 16 divided by 36. You could reduce that to 4/9 if you wanted to. E, a multiple of 13. Well, multiples of 13, there's only a couple. There's 13. There is 26. And is there one more after that? No, there's no 39. So there's only 2 multiples of 13. So that would be 2 out of 36, which could be rewritten as 1/18 if you wanted to. Okay. All right, G, a multiple of both 4 and 6. A multiple of both 4 and 6. Okay, so first I think we're going to have to list multiples of 4 and 6. We'd say there's 4, there's 8, there's 12, there's 16, there's 20, there's 24, there's 28, and there's 32, and there's 36. Now, which of these is a multiple of 6 also? 12, 24, and 36. So only 3 of them. So this would be 3 divided by 36. Could also be written as 1 divided by 12. Okay. 5. We're going to do A, and then we're going to B1 and B3. B3. Okay. So list the 6 different orders in which Annie, Kai, and Nada may sit in a row. It's always handy to use names in these problems that start with different letters so that we can make abbreviations. Nice that they used A, K, and N. List the 6 different orders in which A, K, and N may sit in a row. So we could list those. Like we did before, let's be organized about the way we do it. So first I listed the 2 possibilities that start with A, then I listed the 2 possibilities that start with K, then I listed the 2 possibilities that start with N. and that keeps it kind of organized. Okay, so those are the 6 possibilities. Now I go to B1. If the 3 of them sit randomly in a row, determine the probability that ante sits in the middle. So let's see, not here, there's 1, and there's 1. So there's 2 possibilities that ante sits in the middle. I don't know if I'm saying that right. Sorry, ante. So that would be 2 out of 6, also known as 1/3. What about the probability that ante does not sit at the right end? So maybe it's easier to see the ones that ante does sit at the right end. So there's this one and this one. The other one she is not. So that means there are 4 possibilities she is not sitting at the right end. So we'll say 4 out of 6, which is also all known as 2/3. Okay. So that's it for page 4. And the next one is page 5. So I'll stop here.